Luciana Benotti is an associate professor in computer science at the Universidad Nacional de Córdoba and a researcher in artificial intelligence at CONICET, Argentina. Her research interests include different aspects of situated and interactive natural language processing, like interpreting noisy user-generated text, generating classification requests, and deciding when to talk in a dialogue system, among others. She's particularly interested in non-linguistic features that contribute to the meaning conveyed during a conversation. Let's welcome Luciana.
Well, I want to thank one more to the organizers of Khipu, although I've done this like 10 times already. But after finishing this week, I feel that for me and for my group, it's going to be like history before Khipu and history after Khipu. So really, thank you for organizing this. So today I decided to show you an application of NLP techniques that I'm very excited about. As Oriol said, this is using NLP, in fact, for processing text that is not a natural language, but should be a programming language. So it's to predict success on programming language exercises. So let me explain a little bit what I mean about this. So all my talk will be about that. But first, what I wanted to just summarize my talk with how could I summarize my talk in just one sentence to the NLP community. So in the NLP community, and I'm going to explain about this, there is this bias in the language models, and there is a lot of people working on how to solve that. But today I want to show an application of how these bias that are there in the language models can be used for a good purpose. So let's start by talking about predicting student success. So this is previous work that was published NIPS in 2017. So in this previous work, we have a learner that is trying to solve a programming exercise online. And she can try several times. So this is an online platform where there are programming exercises, and the student can try as many times as she wants. So the task that this previous work addressed is to predict whether she will successfully complete that exercise or abandon it. So one programming exercise, right? And then in order to address this problem, they have a history of attempts from that student. This is the code. It's a block-based language that is designed for children to learn programming. And these block-based language programs are encoded as abstract syntax trees. So this is the abstract syntax trees of the program, and then they are fed to a long short-term memory network. So in this work, they have several baselines. So the most simple baseline is to always say success. So this is a very simple programming language. I will show a little bit more about that. And only with saying success, the accuracy is quite high. And then they do feature engineering on exercise history and student history. And then they propose this architecture that I showed you before that they call deep knowledge tracing, and they get like impressive performance on this task. But also we have to take into account how this performance, so this is a team, so it's like an improvement of from that baseline, yes? How it improves from that baseline. So the programming language that they are working on there is called Blockly. And this is what students see when they are trying to solve the exercises. So here, what the student has to do is to make this bird go all the way to the little pig. And in order to do that, there are some commands in the programming language that the student can use. So one characteristic of this block-based programming language is that they compile always. There are no syntactical errors because of how the students build the program. So everything that they can put here is a correct command. It's a command that belongs to the language, and also if they don't put it in the right, in the right combination, it doesn't match. It's like a puzzle, right? So it doesn't fit. So everything that they write is a program, and it compiles. This is important for us because we have a different problem. So what we are trying to address is when a student is learning a programming language in which that student can type freely, but it's just starting. So suppose it's the first year for that student that ever sees a programming language. It's the first programming language for that student. And here we have this platform that is called Mumuki, where the students can do the same that I said before. So in this part, they can write a solution to the exercise that is explained here. So this is an exercise that is asking the student to program the leap year function to verify whether a year is leap or not. Here is the instructions, the definition, and an example. And this is where the student writes a solution. So this is a correct solution. The platform tests whether this compiles. And then it has some test cases defined. And if the solution passes the test cases, then this is marked as green, and the exercise is correct. Otherwise, red, like light red, is that the test cases are not passed. And this other more darker red is that there is a compilation problem, so the syntax is not good. So in this kind of setup, there are many more possible programs that a learner can write because we have free text than in the previous work. And importantly, half of the programs that we see in our data sets do not compile. So we cannot build an abstract syntax tree, right? So looking at these programs that the students write, and the wide variety of errors that we see, and the creativity that we see in those errors, we thought, how about treating this code from the learners as a natural language? So in order to get the intuition, I gave here some examples, some made-up examples of different utterances that show how fluent is the producer of this, the speaker of these utterances, right? So suppose this is a student that speaks Spanish and is learning English. So here, in the end, we have a correct way of saying, I made the big bets yesterday morning, and as we go up, we see some different sorts of errors. So here, the adjective is in a plural. That's a typical error for Spanish speakers to make adjectives plural, because in Spanish, adjectives are plural. Then as you go up, also here, so in English, you have to say, you made the bets. You don't do the bets, right? And that's a typical error in Spanish, because we only have one verb for saying that. And well, the first one, we already see interference at a lexical level, like using words in Spanish for the verb, for instance, in this case. So here I show you an example of the same kind of evidence of fluency, but in this case is on the Haskell language. So here, suppose that you have students that have English as a native language, and then they are learning Haskell as their first programming language. So in the last line, we see a correct program for the leap year function. And as we go up, and these, in fact, are not invented examples, are examples that we see in our data set. They use functions with the wrong number of parameters, the syntax, so they have 2 equal signs, and that's not possible in Haskell. Even you see some students that have no clue what to do, and they just try to copy what they see on the left to the right text box. So one intuition that we had too is, and this relates to the one sentence that I showed you at the beginning, is there is this technique in natural language processing called word embeddings that is a way of representing the semantics of words. And so these are a language modeling technique. And the meaning of natural language word is learned by reading this large volume of text, as they mentioned before, like whole Wikipedia or a lot of news. So we had these word embeddings trained on English, news, and Wikipedia that can answer questions like this one. Rome is to Italy as Paris is to France, right? And these kind of embeddings also answer these other questions in a, so what do you think is going to be the answer to this question? If you ask a model trained on Wikipedia and news in English. So this is a problem. This is what we call biased word embeddings. So we know that these models, like word embeddings, are able to capture these errors. And also, there are arguments that say that, in fact, these models kind of make these errors deeper. They enlarge them, right? So the idea of this work is to use this problem that these models have to train Haskell, to train them over learner code. In this case, we are using Haskell because that's what we had the data for. So what we see when we learn these word embeddings is that we can ask the model questions like, 2 is to integer as to A is to what? What do you think the answer is going to be? Hmm? Well, in Haskell, sure. So in Haskell is character. So this is a character, right? And then we have other questions like this. Plus is to 0 as or is to what? So what's the neutral element of this? Hmm? So it should be false. But we are trained on learner code. So it's picking up errors, very frequent errors that we find there. So here we have an error, as also the previous one, like nurse, there was an error, right? Or what we say in pedagogy, a misconception, yeah? Because it's not something that is completely out of focus. It's a typical error that is very typical to think that the neutral element of or is true. So if you want to, I just wanted to make the link to what we saw before during Khipu. So these word embeddings I'm talking about is the same as continued, so it's the continuous vector space technique. And I just wanted to remind you the references that Cho gave us on Wednesday, I think. So the architecture that we have is we annotate the training set by looking into the future to see whether the student actually succeeded in the exercise or dropped out at the exercise. So dropout would be that he left the exercise in a red state and didn't reach the green state. We process each attempt program as a sequence of word embeddings, and we feed that into a long short-term memory network. So it's a pretty simple and standard architecture for binary classification to check whether, to predict whether the student is going to succeed or drop out that exercise. We have two data sets. One data set is a classroom data set with 75 students. The other has 4,000 students. It's a massive online course for learning different kind of programming languages in this platform, Mumuki. The number of exercises is fixed. It's the same exercises in the two data sets, 63. And then we have the bigger data set is more than 10 times the other data set. These are each of the attempts from the students. And you can see also the difference in the vocabulary size. So this is a simple histogram of the times in which the students make the attempts. So you can see that here the students make most submissions in the morning, that is the time of the course. So they are using the platform during the course. In fact, these are my students, first-year students of a computer science degree. They are around 18 years old or older. And then the students here are people that connect probably after work, because most submissions are after 7 p.m. And then we also had like the simple baseline of Owen saying success in the two data sets. Then we have also a baseline 2 and baseline 3, where we did extensive feature engineering with a team of pedagogues trying to predict which are the features that affect the success of the students, capturing the history of the student or how hard the exercise is. This took us a lot of time to build these baselines. And in fact, the improvements were incremental. We did ablation studies, but I'm not going to get on those details. And then in 1 week, we decided to implement that approach that I told you about, and we got like an impressive improvement from the work that it took us. Also, we evaluated human teachers' performance, and for this, we gave the exercises, the attempts to 2 human teachers, and the performance of the human teachers there. So I was one of the subjects because this was the work of one of my students. And it took like 3 hours to make the annotations for only 50 attempts of exercises. So our performance is not only lower for this task, but also it takes us much more time. So finally, just to show you an example of one exercise, here we have what we saw at the beginning of different submissions on the leap year exercise. The one that you see in the bottom is a correct submission. And this other one is almost correct, but parentheses are not balanced. So in this case, for instance, Mumuki would say that this doesn't compile, but the classificator is able to realize that this student is probably very probably going to solve this problem on his own. So this is predicted to be a success, right? And then we have here this confusion between conjunction and disjunction. So this should be a disjunction and it's a conjunction. But again, the system realizes that there is a problem here, but says that maybe this student will be able to solve this problem on his own. So this is where the model draws the line, and the ones above this are predicted as needing external help in order to be able to solve this exercise correctly. So in conclusion, the big message behind this is bias in language models can be used for good. If we know that our data set is biased, if we know that our data set has some, so it's, for instance, learner information, then we can use that to detect their errors And in this case, we use them for predicting whether a learner will successfully complete an exercise in a text-based programming language. As I mentioned before, when you see the learner's code and you see the correct solutions, there's not a lot of variability because these are simple exercises. But when you see the incorrect solutions, you see a lot of variability, a lot of creative. Students are very creative to make errors when learning to program. And these errors are nested. So standard error detection techniques used for compilers don't work, and they don't help very much the learners. For future performance, so now for future work, so now we are only reporting using one attempt. So we don't see the history of that student in the model that I presented. We could try to add the previous submissions of the same student on the exercise to see how that student is progressing. For instance, one of the things that we looked into with the pedagogues that we work with is that there are some students that plan ahead and make big changes to the exercises, and then there are others that change 2 characters and then send the exercise again. So pedagogues say that you have planner students and tinker students, and this could be taken into account by sending previous attempts or by integrating the features that we did feature engineering. And another line of work that is starting now is that language models obtained in this way can be used as synthetic students for control experiments for the area of education. And just a small update on future work. So I said that we were trying to use previous attempts, but this is not working for us for the moment. I mean, this is last minute report. And I was wondering whether this was related to this recently published work in which, so this work shows that transformers and other networks like LSTMs forget the history when the history gets very long, right? And they are not able to be sensitive to shuffling and different techniques that destroy the context. So just, thank you.
All right, I think we have time for a couple of questions. Anyone?
My question is related to the abstract syntax tree. Did you use classic compiler techniques like defining the grammar and the tokens for the abstract syntax tree, or are you using some learnable or machine learning techniques for finding the correct grammar of the programming language?
So in previous work, they construct the syntax tree using standard techniques from compilers because they have programs that compile. In our data set, half of our programs don't compile, so we don't even try to construct the abstract syntax trees. We directly apply, we consider the code as natural language. We just tokenize it, and we build the word embeddings. We don't build the abstract syntax tree.
Okay, thank you.
Okay, any other question?
Hi, do you think these kind of word embeddings can generalize to bigger problems, let's say, not in the first year, but in the second year when they're working on bigger projects? And also if you think that they could generalize to different programming languages?
Well, these are very good questions. So what I'm worried about, I mean, these are very short programs, right? I mean, they have 2 lines, 3 lines of code, maybe 5 lines. So I don't know how these models will generalize when the context is getting bigger. So it's exactly what I mentioned in the end. So how much information can we feed into these systems that they can take into account a context that was like very far away in the past. And then this is related also to your second question, because if we move to another programming language, so at first I thought this should work for any programming language. But then if the programming language is more verbose, if it, like for instance, Haskell is you can write programs that are very short. It has a syntax a bit similar to Python, although it's a different paradigm. But if you go to a language that is verbose, like Java, and you have very long programs, maybe that could start to be a problem. So yeah, it's interesting as future work.